Hello everyone. Let us continue the next topic from the fifth module, energy methods and columns. So the next topic is strain energy due to bending. For that, let us understand. Consider one simply supported beam on which there is one uniform distributed load for its entire span. So the uniformly distributed load magnitude is W kilonewtons per meter. Now let us consider two sections on this simply supported beam, section 1 1 and section 2 2. So if we zoom out this particular area, we can see that there is a section 1 1 and section 2 2 which are apart by a distance dx. So in that particular section, let us consider one element of cross section dA and length dx. So when we consider that, let us define the distance of centroid of that particular element from the neutral axis. Let that be y. And the maximum limit of this particular centroid will be on the upper side, it will be y subscript O, and on the lower side it will be y subscript T. So once we understand this diagram of a simply supported beam and a section with an element, let us understand mathematically. So here the bending moment equation I have used. So that is nothing but m by I is equal to stress by the distance y, which I rearranged like this. And I also know a strain energy equation in terms of stress. So it will be sigma square volume divided by 2 times Young's modulus. Now please understand, when I am using strain energy means it is within elastic limit. Now when we say strain energy, there has to be deformation, not deflection. But when we use a simply supported beam and when we apply a load from the top, that there is going to be deflection at the bottom in the downward direction, whereas it is not deformation. Whereas for strain energy we need a deformation. So how exactly we are going to understand this? When the load is applied from the top on this particular beam, so that is nothing but on this particular element, when we say, so if it is above the neutral axis, there will be compression acting. If it is element is considered below neutral axis, it is going to be tension. It is just like the experiment what we have done, Wagner beam, where the strain gauges or the strain gauges what we have used, some of them undergo compression, some of them undergo tension. Similarly, when the load is applied from the top, above neutral axis it is going to be compression, and below neutral axis it is going to be tension. So that will lead to deformation at the elemental level. So it is not deflection anymore, it is deformation. So for strain energy I am writing an equation in terms of stress, and again I am deducing the strain energy equation for an element first, which I will then use to find the strain energy for the entire beam. So strain energy I have rewritten, and the volume of that particular element is cross sectional area dA and the length dx. Dx is nothing but the distance between two sections or the elemental length dx. Now by substituting this stress and the volume in the strain energy equation, I'll get an equation here where movement which is constant for the element as well as for the beam. So it is constant, and the distance of y depends on the location where I am considering the element, and dA is cross sectional area which depends on the thickness and the width, the other dimension, and dx is nothing but the length. Now Young's modulus is again constant, and moment of inertia, I am considering a rectangular element, I need to deduce the moment of inertia of that particular element. Now this is rectangular element, whereas the if the beam cross section is also rectangle, then the moment of inertia will be easier to deduce. Now once I get the strain energy equation for an element, I can deduce the strain energy for the entire beam by summing up many elements like this, or by putting an integral sign for a limit for first length, that is dx. If I deduce for entire beam, so dx has to be written in terms of length, whereas dA will be written in terms of dy if I consider it to be two-dimensional, or I have to define the another dimension as well. So using this equation, I can deduce strain energy due to bending. So let us understand first. I have used a bending equation, then I have used the strain energy equation. I have considered a small element here of cross-sectional area dA and a length dx. Now if I want to find what is the centroidal distance from the neutral axis of that element, and if I mention what is the limit it can go for, then using all these parameters I can write strain energy using stress due to bending and the volume of that element. I can write like this, and integrating multiple elements or integrating for the given limit as well as for the length, I can deduce strain energy due to bending. We will solve some more problems on this which will help you to understand this even more better. So I hope this is clear. If you have any doubts, please let me know. Let us continue the next topic in the next video. Thank you.